So thank you so much for inviting me to come. So I'm really going to shift gears, I think, a little bit from what we've been hearing about and talk about a recent discovery that we made of globular cluster candidates in a redshift 2.5 galaxy. Before I do that, I wanted to just take a moment to thank the fantastic folks that I have the pleasure of working with at UMass, shown here, working on a really wide range of stuff. Globular clusters is a very new topic for me. So they're working on a lot of other stuff related to galaxy evolution that I won't mention today, but really doing some fun work. Okay. And also, I'll call it a few times, but Sam Culler, who is here, soon to be doctor in a few weeks, I'll talk about some of the work we have done collaboratively. Okay, so shown here is a picture of M92. M92 is one of the brightest and oldest globular clusters in our Milky Way. It is visible to the naked eye, and it was first discovered in 1777, and the individual stars in M92 were first resolved by William Herschel in 1783. So we have known about these objects, about globular clusters, for centuries. And so why is it that we still don't really understand how they formed? And so I hope to argue today that looking towards the early universe is going to be really informative, I think, starting now with all these Webb observations and moving forward in terms of unraveling and learning more about these clusters. So shown here is a timeline, Big Bang on the left, and then fast forwarding 13.7 billion years to the present day on the right. It is not linear in time. So we know just by, well, age dating is tough, but if we look at local clusters, we think that they formed about 11 to 13 billion years ago. So if I were to put that on a redshift space, we think that the first globular clusters were probably forming, I don't know, roughly maybe somewhere around a redshift of 8 to 10, and then, you know, that range might extend down to something like redshift 2.5. And so I'm calling this the epoch of globular cluster formation here. And so if you were to find a globular cluster at, say, redshift 8 to 10, you'd expect them to all be very young blue stars, right? It's just formed. However, if it formed, and so this is only 700 million years after the Big Bang, they formed, and then you just let them passively evolve. About 2 billion years later, which would be redshift 2.5, you would expect that these clusters already would look quite old, very red. All those young stars have died away. Okay, however, we're still in this epoch of globular cluster formation, so in principle, you could still be also forming new clusters, and you might expect that you could see a range of young clusters and older clusters at this point. So in comes the data that we were looking at, and this came from the Uncover survey. I highlighted a few of the folks who are here in the room on our team, and I just wanted to give Uncover and Mega Science a shout out, lovely group of people to work with, and also encourage you to go see Sam's poster, which will be up Wednesday and Thursday on low mass quiescent galaxies. So within this data, so here we have the Uncover field, I'm going to zoom in on one particular galaxy, which we have nicknamed the Relic. The Relic is a bit more massive than the Milky Way is today, but it formed much more rapidly, forming most of its stars within the first 2 billion years of the universe. And also, unlike the Milky Way, so sorry, I should say which one's the Relic. That's the Relic, in case it wasn't super obvious. It has, so unlike the Milky Way, it has a smooth elliptical profile. So these you can ignore these two galaxies. They are not at the same redshift as the So let's change the contrast level here and draw out the light here. And so what we see, or maybe what you can see sort of hinting here, are a bunch of little clumps surrounding the Relic. So the Relic has this is the direction of magnification. So it's 2.5 in this direction and only 1.1 in this direction. And you can see this, maybe you can see this tidal tail extending down to these low mass companions down here. The Relic is in an overdensity behind the Abell 2744 cluster at redshift 2.5. There are hundreds, surprisingly, of galaxies at this redshift behind this cluster. So it's a big overdensity, and it has suppressed star formation. These two little companions down here are less than 10 to the 9, and varying degrees of suppressed star formation, but a little bit more enhanced relative to the relic. Okay, so now what I want to do is remove the light of those neighbors that are not, so I've removed the neighbors that are not at the right redshift, and now I'm showing you this globular cluster population that we're seeing here. However, that diffuse light from the main galaxy kind of makes it tough to find them, so let's remove that too. And so what I hope you can see here is not only encircled all of these little clumps surrounding this galaxy, but really remarkably, the wide range of colors that we're seeing of these different clumps. And so we think that these are globular cluster candidates with a really wide range of age, from only tens of mega years up to over 1 billion years old already. So we have, Sam is leading a cycle 3 program to get deep IFU spectroscopy, in particular of this region here. So I encourage you, as well as shall remain pointing, I encourage you to stay tuned. I'll just show you a quick sneak peek to hopefully convince you at this point that these are bona fide clusters associated with this galaxy. So the ones that, this one in particular, that is not associated, but just to orient you, this cluster right here, we're seeing an H alpha at the same redshift as the galaxy, as well as some helium emission from that young cluster. Okay, so stay tuned for more spectroscopic, but what I'm going to focus on here is showing you the results we have from looking at the photometry and modeling that. And so here, each of the clusters is now circled. The color of their circle is their age. And so this is plotting the stellar mass of each of these clumps inferred as a function of their cluster age. And what you'll notice is, so we see here that the most massive clusters are also the oldest, and so you're seeing a mass to light effect here in terms of sensitivity. And what we've also done here is compare to some globular cluster simulations at this same epoch. And the point here is to really demonstrate that we are consistent with seeing sort of these outliers and this idea that we're looking at the tip of the iceberg in terms of seeing this and detecting this globular cluster population. But really quite remarkable and a very subtle effect that you could just very easily miss if you didn't have a keen, close eye looking for them. And so one of the really interesting things that you can do with this cluster population is reconstruct, based on their ages, the formation history of this population. And so this is what I'm showing you here first for the main galaxy, so the central light associated with that host galaxy. And so this galaxy formed quite rapidly within the first, within a few billion years, and then quenched, and this is sort of a modest star formation rate. It's about just under a dex under the star formation main sequence, and perhaps you can see this big uncertainty here might be associated with that tidal interaction with those neighboring galaxies that happened quite recently. And so if we link this to the cluster population, what we think we're seeing is that those older clusters are formed in situ, and the younger ones were perhaps accreted or a consequence of that interaction if they were to have the galaxy took gas from those neighboring galaxies. So just using the ages and masses of these clusters, you can predict the cluster-based star formation history. And so modulo large uncertainties, what you'll notice is that it's quite enhanced in this period when the galaxy, the main galaxy, is otherwise more suppressed. And so I think this is showing some tentative evidence of separating in situ versus ex situ accretion of these clusters, the ones that formed inside the galaxy as opposed to ones that then later were accreted. So at this point, you might also be skeptical and say, well, Kate, those were some pretty high masses. Are those really globular clusters? If I didn't convince you by saying they're just the outliers. If we look in the nearby universe, there are examples of clusters that are quite massive, similar to those we see in the relic, and it happens in post-mergers. So this is a post-merger NGC34. This is work by Angela Adamo. And you can see a lot of similar features, a similar range of dynamic range of the ages of the clusters. And then also you can see this, for example, is 10 to the 8, so this big honkin' cluster in this galaxy. And one of the really striking things is this very young population, similar to what we're seeing in the Relic, that was formed from a stream of gas that was stripped during the interaction. Now, this plot is showing you the specific frequency of globular clusters as a function of the absolute V-band magnitude. So over here are more massive, something like elliptical galaxies, and on the right-hand side would be dwarfs. And up here, you can see these are the populations that seem to have an excess of globular clusters. And so it's been known that both dwarf galaxies tend to have a higher specific frequency, but also the most massive galaxies. And I think this is sort of where, for me, it circled back to other areas that I have been working on, that it's really quite striking, is using these massive ellipticals as a laboratory to try to understand their formation history and separating out in situ and ex situ formation. So we think that the Relic is hosting over a dozen of globular cluster candidates, and they're consistent with the largest ones that are formed in these models. It's showing you a really early universe example of what we already have been seeing in the local universe from these. So I wanted to sort of step back from this case study and put this into a context. So this is a work in progress. There's a lot going on here. I'm not going to go into all of this right now. Yep. And so this is showing you sort of a evolutionary framework of massive galaxy formation, split into those galaxies that form and quench very rapidly on the top, and those that have a slower formation and quenching timescale on the bottom. And so what I first wanted to highlight in the context of the Relic is really this end stage here, where we think that all massive galaxies, once they quench, grow and have late stage mergers and accretion. And I think this is most nicely demonstrated by work here that was led by Allison Hill in 2017, and looking at this, the puff up of these galaxies and their outer envelopes over billions of years of cosmic evolution as they are on average getting larger and seeing this size evolution. And so we know that these massive galaxies are going to be merging and accreting, right? So you have this other population that can now serve as a probe, sort of separate and independent to understand that process. Similarly, if I just show you now this fast track to quenching, here, there's lots of ways that you can rapidly quench a galaxy. And the idea here is that something has to drive the gas to the center of the galaxy so that it's very concentrated. And so one of the canonical pathways is through a major merger. And in this case of a major merger, you would form very rapidly in situ. You'd have a merger and very quickly quench the galaxy. So stepping away a little bit from globular clusters, just to highlight some work by the PhD student Sarah Badansky at UMass Amherst. I think that we're seeing interesting evidence, possibly, that's linking this phase, this dusty star-forming phase, with quiescent galaxies. And what you're seeing here is when we look at 444 at 4 microns with J/T, that the light profiles, if you were to compare them, so this should be more closely tracing the stellar mass, that dusty star-forming galaxies already look very similar to massive quiescent galaxies. And so perhaps, it's long been thought that there is an evolutionary link there. And so they have formed. The stars should be there. They should be ready for this transition and quenching relative to those that are not similarly massive, but not as dusty. Okay. Other evidence that we're seeing, just to flash by really quickly, also is a lot of new exciting observations spectroscopically with Webb, finding, for example, neutral sodium in absorption blue shifted, suggesting neutral outflows and providing some empirical links between quenching and AGN, which I think are really quite exciting. So again, pulling this back together and returning to the story I told you in the beginning about the relic, this is a new area for me, and so I'm keen to hear the perspective of folks and your knowledge of globular clusters, but I think that these high redshift laboratories, and in particular massive quiescent galaxies, using this deep data is a really interesting new direction to be able to understand this evolutionary picture over most of cosmic time, and gives us a chance to not only look backwards, but also to think about looking forwards with them. And so in my final minute, I'll move back to this slide. I wanted to take a moment to advertise a program at the Cosmic Dawn Center. The Dawn IRAS Scholars Program, I don't know, has anyone here, did you hear, so we ran this from 2019 to 2022, I think. Has anyone heard of the Dawn? Okay, a few hands, excellent. So we've been trying to get it renewed, and in a bit of good news, in all of the funding last week, so I was told that it was rejected months ago, but never actually heard. And then last week I got a lovely email saying that it was awarded. So, surprise. So we're really excited that we will be restarting this program, and I just wanted to take a moment to highlight to you guys that you should, for those that are graduate students in the room or undergraduates, please apply. For those of you who have students who work with you, please let them know. Happy to send you flyers to advertise in your department. This is open. We'll have a cohort of 5 undergraduates and 2 graduate students. The idea is that the 2 graduate students get ample opportunity in leadership and mentorship in leading weekly workshops and working with the undergraduates and continue their thesis work. So they're not starting a new project, whereas undergraduates will be paired with folks at Dawn. So excited that that will be coming back online. Okay, I will end here.
I start. Just a comment. If you look at our own galaxy, the older population of GCs may look poor and more extended. So if you're proposing these are more in situ form at a high redshift, you might expect to be more concentrated.
Yes. So if you look, oh, hold on, I got to go back to the image. So, so first, it's a bit of a trick of the eye that you have to be aware that it is more extended along this axis. So this is a factor of 2.5 and not that way. So these are actually, if you saw it in the source plane, just kind of reimagine that these are actually fairly close in to the center. And this is where you're seeing all the old ones. So pretty close in. And a lot of the younger ones are sort of scattered throughout the halo and a couple sort of mixed in. Exactly correct that if we could constrain metallicity, you might expect to be seeing the similar effects like we're seeing locally with low metallicity and more metal rich. That is something that we see vaguely tentative evidence for, if you want to believe it from photometry. And that I hope we can say more, maybe, with the spectroscopy about metallicity. Thank you.
All right, we'll do one more question while Crystal sets up, I think.
Part of the idea for low redshift globular cluster studies is that these high specific frequency ellipticals are kind of a product we call bias formation, that early collapsing higher densities of star formation were productive of making globular clusters. And that applies not just to the in situ population, but they also have these big accreted stellar halos you talked about later. Say after redshift of 1, they were accreting stuff, satellite galaxies, but those should also have high specific frequency. They're biased. They also form in that high density early environment. So what I'm wondering is if now if you look around in that high overdense environment there, you would expect in this picture to see other kind of potential satellites that also have high specific frequency of protoglobular clusters. Have you looked for that?
That is a great question. We have, we did the same, using the same methodology, we have looked at the other galaxies behind Abell 2744, And we absolutely do see them. Have we done it in a systematic way? No. Will we? Yes. But we do definitely see that there are other, also similarly massive ones hosting it, but it's not, this point very well taken, and if only there were infinite time. Thank you.
All right, let's
Oh, there
thank
we go.
Kate one more time.